chain rule is used when we have a composition of functions. So it allows to differentiate complex functions. So by kind of differentiating the inner function first, then differentiating the outer function. So for instance, the complex function, for instance, if you have y equal to, for instance, maybe 3x squared plus 5 raised to the power of 8. So when we want to use chain rule, we always say that our inner function should be our u. So we have like u is equal to 3x squared plus 5 for this case. And our y will just be, so instead of this, we have u. So it's just u power 8. So what we do is we differentiate this with respect to x and this with respect to u. So if you differentiate this with respect to x, du dx will just be 2 times 3, which is 6x minus 1, as x bracket 2 power x power 2 minus 1, which is just 1. So we have 6x. Differentiation of 5 is just 0. So this is 6x. And here we differentiate y, dy. Since we are differentiating it with respect to it, then we'll have over du. Then this will be, we write our u power 8, we take 8 here and we subtract 1 here. So this is 8 u power 7. So we have, so our dy over dx and chain rule is just, this is the outer differentiation and this is the inner differentiation of du. So it's just dy over du times du over dx. So this outer times the inner differentiation, and in this case it's just 8u power 7 times inner differentiation 6x. So then this is equal to 8. We can multiply 8 and 6. So if you multiply this 8 by 6, we'll have 8 times 6, I think is 48. So this is 48 u power 7 x, and this is 48. Remember our u is 3x squared plus 5, 3x squared plus 5 power 7 x. Then that's all. So now we have the formula for the chain rule. Dy over dx is equal to dy over du times du over dx, where u is the inner function. In this example, we have y equal to this 4x squared plus 19 minus 5. So for this case, we let our u to be the inner function, which is 4x squared plus 19. 4x squared plus 19. Then we have our y will just become u, because instead of this 4x squared plus 19, we can just write it as u power minus 5. Then from here, we have our du over dx will just be equal to, we have our 4x squared. We take this power 2 here and multiply it by 4. Then we subtract 1 from the power, plus 19 is constant, so its derivative is 0. So you have 2 times 4, which is 8, and x power 2 minus 1 is 1, so x power 1 was just 8x. So, and for this one, then we differentiate y with respect to u, since with respect to u, the inner function. So then this will be u power minus 5. I will take minus 5 here, and from minus 5 I will subtract 1. So we'll have minus 5 u power minus 5 minus 1, which is minus 6. So now we can use our formula. If you remember, our formula is dy over dx is equal to dy over du times du over dx. So our dy over du is minus 5 u power minus 5 minus, sorry, just minus 6 times du dx is at x. And from here I can multiply 5 and 8, I will get minus 40 u power minus 6x. and this is just minus 4t. Our u is 4x squared plus 19 power minus 6x, and that's all. In this example, we want to solve y is equal to square root of s cubed minus 2x. So the first step whenever we want to solve this is to make it in the form, the square root in just the same as s cubed minus 2x raised to power 1 over 2. It's just the same as this. So if we make it like this, then we can, using our formula, we remember that our formula is dy over dx is equal to dy over du times du over dx. So we have to identify our u first. So we say u is whatever we have in the inner of the function. So u is the inner function is s cubed minus 2x. Then outside we have y equal to u power 1 over 2. So instead of this x, this u that I have here, this one I just substituted with u power 1 over 2. Then I differentiate the u first, the first one, the inner function, and I will have du with respect to x. I'm having it's a function of x. Then this is equal to, if I differentiate s cubed, it's just 3x squared minus 2x. Remember, if you differentiate a constant function, it's just 2. And if you differentiate, a function with just constant and x is just the constant. And for this one, I will have dy over du is equal to u power 1 over 2. I'll take the 1 over 2 here and I'll subtract 1 from it. Then I'll have a 1 over 2 u power 1 over 2 minus 1 half minus 1 is just minus half. And this one, if I like, I can easily write it as 1 over 2 times this one. I can leave it like this, or I can write it 1 over u power half. So I will take the u power half, I will remove the negative, but I have to take the u power half as the denominator. So I have 1 over 2 u power half. So now I can just use my formula. Dy over dx is equal to dy over du times du over dx. Dy over du is 1 over 2 u power half times du over dx times 3x squared minus 1. And this one I can just write it as 1 times this is 3x squared minus 1 over 2. Our u is, if we can substitute our u back, which is 3x cubed minus 2x, so s cubed minus 2x power half. And this one I can just write it as 3x squared minus 1 divided by here 2. This is power half, so I can use this substitution that I use here. I can use it back again. This one power half for the root, I can use it back again. So if I use it back again, I will have a 2 square root of s cubed minus 2x. Differentiating exponential function. So if you have your y is equal to exponential x, then your dy over dx is just exponential x, just the same. So if y is equal to exponential x, dy dx is just the same exponential x. So for instance, if you have y equal to 2 exponential x, dy over dx, you know, this is just a constant, it will still be 2 exponential x. And if your y is equal to exponential, like here, exponential, some constant exponential, some constant r and x, then dy over dx is just equal to r a exponential rx. This is just your r times your y again, which is a exponential x. So it is just saying that if you have, for instance, y is equal to 2 as, let's even start a simple one, y equal to maybe exponential 2x. Here your a is 2, the constant, your a, sorry, is 1, the constant. So what is just saying dy over dx is just take this constant, that is coefficient of x, back here and just write exponential 2x. That's all. So it's just 2y. So, and similarly, if you have y equal to exponential minus 3x, then dy over dx is just equal to take the constant here, minus 3 exponential minus 3x. Similarly, if you have y equal to 4 exponential 5x, then dy over dx is just equal to take 5 here times 4 exponential 5x. So it is 20 exponential 5x. So let's look at this example here. You have y is equal to exponential 3x. As we said, y equal to exponential 3x. So dy dx is just equal to dy over dx is just equal to take this 3 and exponential 3x. That's all. So similarly, y equal to exponential minus 2x. Take this minus 2 here. Then you have dy over dx is equal to minus 2. Take it at the right hand side of the exponential, and exponential minus 2x. So now we want to differentiate this. So now if you look at this one, it's not either just some constant times x at the exponential. We have y equal to exponential 2x squared minus 6. So it's not like the other one that we just have a constant like 2x or 3x or 4x. So for this case, we have to use chain rule because we have kind of a function here again. So if we remember, chain rule states that dy over dx is just dy over du times du over dx. So you have to find u. So our u is just our inner function always. So our u, we take it as 2x squared minus 6. Then we differentiate this u. It will be du over dx is equal to this one 2x squared. So it will just be 2x squared. We take this 2 here and multiply by 2 and subtract 1. This is constant, so it's just its derivative is 0. So this one will just give us 4. 2 times 2, 4. X 2 minus 1 is 1, so it's just 4x power 1, which is just 4x. So then our y is just exponential. Here we said it is this. We say it is u, so we just write u. So this one. So instead of 2x squared minus 6, I just substitute u. And remember, dy over du will just be exponential u. If we remember, if y equal to exponential x, dy over dx is just the same exponential x. So similarly, y is equal to exponential u, dy du is exponential u. Then our dy over dx will just be dy over du times du over dx. So this is our dy over du is exponential u times du over dx, which is 4x. And this is exponential. What is our u? So whenever we are multiplying by exponential by something, it's better to put this behind exponential. So 4x exponential u. And this one I can just write the 4x exponential. Let's substitute back our u. Our u, we said it is 2x squared minus 6. So this is 2x squared minus 6. Differentiating a logarithmic function. So when differentiating a logarithmic function, if you have log ln x, or which is just the natural log e of x, then dy over dx is just 1 over x. So whenever you have maybe y equal to 2 ln x, so dy over dx is just this 2 times the constant ln x. We know it is just 1 over x, so this 2 over x. So this is just the logarithmic function. If you want to differentiate ln x, is 1 over x. If you have y is equal to ln u, for instance, then dy over this du is just equal to 1 over u. If you have h of x is equal to ln x, the h of x over dx, which sometimes we just write as h prime of x is just 1 over x. So let's start with this example. Find the derivative of y equal to ln 2x. So if you look at in this example, we don't have a just x. If we have x, I can just see one. Like if y is just ln x, as before, we can just see dy over dx equal to 1 over x. But if you look at this, is ln is having another function 2x inside. So we use the chain rule. So here we use chain rule. Then remember, chain rule is dy over dx is equal to dy over du times du over dx. So we write it so we have to find our u. So for here we see our inner function 2x is du. Then we just write find du dx. And remember, this is just a constant times just x power 1, so it will just be the constant 2. And from here we have our, from this y equal to ln 2x, I can just write it y equal to ln, instead of 2x I can just write u. So y is equal to ln u, and therefore if I want to find dy over du, then from what we have above here, it is just equal to 1 over u. So this is just equal to 1 over u. Then we can use now our chain rule. Dy dx, using our chain rule, we have is equal to dy over du, which is 1 over u, times du over dx, which is 2. And 1 times 2 is 2 over u. And remember, what is our u? So is 2 over our u is 2x. 2x. 2 goes into this 2 one time, so we'll just have 1 over x. So from here we got a rule that whenever you have y equal to ln of some constant ax is also equal to 1 over, so it is dy over dx is just 1 over x. So for instance, if you have y equal to 5x, then dy over dx, so dy equal to ln 5x, dy over dx is just 1 over x. So let's look at this example. We have y equal to ln x squared plus 4x. So if you look at this one, we also have to use chain rule, which says dy over dx equals dy over du times du over dx. So using this chain rule, we have here we have to find our u. So our u is what we have our inner function, which is 3x squared plus 4. Then we differentiate it. Du over dx is just here 3x squared, so we have 3x squared. This 2, I take it here and I subtract 1 from here. This is 4 is constant, so its derivative is 0. 2 times 3 is 6. Here x2 minus 1 is 1. So this just x power 1, which is just 6x. So then from here that I have y equal to ln 3x squared plus 4. So instead of this 3x squared plus 4, I can just write u, since I said u is equal to 3x squared plus 4. And if you remember, then dy over du, this is ln u, is just 1 over u. Then we'll just have dy over dx is equal to, so it's equal to dy over du times du over dx, which is dy over du is 1 over u that we got here, times du over dx, which we get here, which is 6x. So 1 times 6x, this is 6x over u. And this is 6x divided by, what is our u? Is 3x squared plus 4. Then that's all. Differentiating trigonometric function. So in trigonometric function, whenever, such as sine, cos, and tan, whenever we have a y is sine x, its derivative is cos x. If it is our y is cos x, derivative is minus sine x. So this one has a negative. So, and if you have y equal to tan x, then dy over dx is equal to sec square x. So this is just saying that, for instance, if we have our y is equal to 2 sine x, this is just constant, so dy over dx is just equal to 2 cos x. If your y equal to 5 cos x, then dy over dx is just, since it is minus sine x, is minus 5 sine x because of the minus here. So an example is, here we have y equal to cos x minus tan x. I want to differentiate this. So we should just remember if the derivative d over dx of cos x, here I'm just saying the derivative of cos x is minus sine x, and d over dx of tan x, that is the derivative of tan x, is sec square x. So that's what we want to differentiate. So we have y dy over dx here. If you differentiate cos x, it is minus sine x, and the derivative of tan x is sec square x. So this is minus sine x minus sec square x. That's all. So here we want to differentiate y sine 3x. If you remember, what we are familiar is, if y is equal to sine x, we know dy over dx is equal to cos x. But here we have sine 3x. So whenever we have a more function here, so because of this function, we have to use chain rule. So chain rule, remember, is dy over dx is dy over du times du over dx. So for this case, we set our u to be this inner function, which is 3x, then dy, sorry, then this du, we differentiate it with respect to dx, and since it's just a constant times x power 1, so it will just be the constant. Then our y is equal to sine 3x. I can just write it y is equal to, since I say 3x is u, sine u, then dy over du, if you remember, if it is sine x, the derivative is cos x. So if it is sine u, the derivative is cos u. Then I can just use my formula now. dy dx is equal to dy over du times du over dx. dy over du is cos u times du dx, which is 3. So and it's recommended that you put this 3 behind here to the right hand side, of course. So this is 3 cos u, and this is 3 cos, what is our u? Our u is 3x, so 3 cos 3x. So the formula is just change y to cos and just multiply it by the derivative of your inner function. So let's look at this. We have y is equal to 2 tan x squared minus 1. The only what we can remember is that we know that if our y is equal to tan x, we know that dy over dx is equal to sec square x. So, but here we have a more complex function, x squared minus 1. So we have to use chain rule. Chain rule states that dy over dx is equal to dy over du times du over dx. So for this case here, we let our u to be the inner function, which is x squared minus 1. Then du over dx will just be 2x, because this 2 come here, and we have 2 minus 1, which is 1. And the derivative of 1 is 0. So, and then we have our y is equal to 2 tan. Now, instead of this x squared minus 1, I can just write u. And if you remember, then dy over du, if we differentiate it, will just be 2. Instead of this tan u, then we'll have sec square u. That is just, it is derivative sec square u. Then now we can use our formula, dy over dx is equal to dy over du times du over dx. and this is just dy over d is 2 sec square u times du over dx, which is 2x, and it's recommended to put this one, multiply this one behind, so it will be 2x times 2 sec square u, and this is 2x times 2 is just 4x sec square u, and this is 4x sec square. Instead of our u, we substitute back, which is x square minus 1, so x square minus 1. That's all. Higher order derivatives. So this is kind of differentiating again and again. So for instance, you have y is equal to x power cube. So this is the first derivative is, if we take this 3 here, we write our x cube and we subtract 1, which is 3x, 3 minus 1 square. So the higher order derivative is kind of differentiated again, that is d square y over dx square. That is differentiating this y twice. So after we find this dy dx, whatever we find now, we differentiate it again. So if we differentiate this, we first write is 3x square, we take this 2 here and we subtract 1 from here, then this is 6, 2 times 3 is 6x, 2 minus 1 is 1, so this is just 6x. So this is higher order derivative. If you like, we can kind of differentiate it once again, d cube y over dx cube. So that is, we want to differentiate 6x. So if you want to differentiate 6x, and this is just 6 times some constants, sorry, 6, a constant times just x power 1, and this is just 6. So this higher order derivative, and if you want to even differentiate this one, this 6, the 6 is constant, so its derivative is 4. So, and d5y over dx5, you are differentiating 0 is still 0. So, some example, find the second and third derivative of this. So, our y is equal to x cubed plus 3x plus 4. So, before we find the second and third derivatives, we have to find the first one. So dy over dx is, we differentiate 3x squared, so we'll have 3 here, we have our x cube, we subtract 1 here, plus 3x, so this is 3 and x power 1, so we'll just have the constant. 4 is 0, so 4 is constant, so the derivative is 0, so we don't have to put it. So this is 3x squared plus 3. So this is our first derivative. So our second derivative is to differentiate this. That is d square y over dx square. This is just d over dx of this dy over dx. So like this is d over dx of 3x squared, this first derivative, that's what we are differentiating. And if you differentiate this, remember we'll just have our 3x squared, but we have to multiply this one by 2 and subtract 1 from 2. This 3 is constant, so it will be 0. So we'll have 2 times 3 is 6 x square. So sorry, 6x power 1. 2 minus 1 is 1. So this is just 6x. So if you want to find the third derivative, x cubed is just d dx, is just differentiating our result from the second derivative, that is differentiating 6x. So, and this is just some 6 times some a constant 6 times x power 1, and this is just the constant. Critical points. A critical point or a stationary point is of a function f of x is just a point where the f prime of x is 0. That is, the derivative of that function is 0. That is kind of, if you plot your function here x, and this is your f of x or your y sometime. So it's the point where this derivative does not change. So somewhere like here it is changing, but it's reached somewhere like the top point or the bottom. So like if we have it like this, so maybe this point and this point, so that's what we call our that's the critical point, the point where the derivative does not change. So whenever we want to find it, that is the point where f prime of x is 0. So for instance, maybe you have a function, example, you have a function y equal to maybe 3x squared plus 2x, and you want to find the critical point. So what the first step is, find dy dx. So if we find dy dx here, we differentiate this, then this will be, we take this 2 here, 2 times 3x 2 minus 1, plus this is 2 and just x, so we just take the constant. Then this is 2 times 3 is 6, x2 minus 1 is just this, plus 2. So our dy dx is equal to this. So to find the critical point, whatever we get here, we say our derivative, we say let it be 0. So we just say our 6x plus 2 to be equal to 0. Then we find x. So this is, if you want to find this, then this implies that 6x is equal to minus 2 if we add minus 2 to both sides, and this x is equal to minus 2 over 6. We divide both sides by 6. This is minus 1 over 3. 2 here, 1, and 2 here, 2 in here, that is 3. So you have 1 minus 1 over 3. So then this is our critical points. So another example is give another example, because you can have more than one critical point. Is maybe you have x squared minus, sorry, s cubed over 3 minus 4x, your y equal to this. So if you want to find the critical point, the first thing is to find dy dx, then that is differentiate this. If you want to differentiate this, we'll have 3, we'll go here, 3s cubed over 3, but we have to subtract 1 from this power, so it will be x squared minus 4x, so this is just 4 if we differentiate, and here 3 will go into 3, 1, so this 1x squared minus 4, so you have our dy over dx is just x squared minus 4. So, and to find the critical point, we have to see our dy over dx is equal to 0. So if it is equal to 0, this implies that this x squared minus 4 equal to 0. And remember, whenever we have x squared minus something, let's try to find, we can write this as x squared equal to 4, and x, we can take the square root here. Since it is even, the power is even, it will be plus or minus 4, and x will be plus or minus 2. And we have two critical points, that is plus 2 and minus 2. So we have this, our critical points are 2 and minus 2. Local minima and maxima occur at a critical point where the second derivative is greater than 0 and the second derivative is less than 0 respectively. So we have a local minima. So let me write this step for finding the, sometimes we call them local extreme, the local extreme. So let me write it. So the first step when you want to find this, find you have a function f of x, find f prime of x, then you set f prime of x to be equal to 0, then you will find x. So suppose you get your x is equal to xa, that is the value that you get for your x, where x is equal to xa, then the next is you should find the second derivative, f prime prime of x, that is differentiate your derivative again. Then substitute, you have to substitute your xa in f prime prime of x in the second derivative. Then you have two options. First, if the f prime prime, when you substitute this xa, that is of xa, if it is greater than 0, then your xa is minima, is local minima. And if f prime prime of xa is less than 0, then your xa is local maxima. So it's just like this. For instance, you have a graph like this. So this is your local maxima and this is your local maxima. At this point, the second derivative here is less than 0. Here it is greater than 0. So let's trace some examples. We want to find all local extrema of f of x is equal to x squared minus 4x. So whenever you see extrema, it means minima and maxima. So we want to find we want to find the local minima and maxima of this function f of x is equal to x squared minus 4x. So the first step is let's write a function. Then next is differentiate this, that is f prime of x. So if we want to differentiate this, we take this 2 here and we have x 2 minus 1 using the power rule, and here is just 4x, so it will just be 4 since x is power 1. So here we'll have 2x power 2 minus 1 is 1 minus 4, so it is just 2x minus 4. So we find our f prime of x. So the next is we let f prime of x to be equal to 0. So that is 2x minus 4 equal to 0. Then we solve for x. So this implies 2x minus 4. We have minus 4 here, so let's add 4 to both sides. And here 0 plus 4. So we have 2x minus 4 plus 4 is 0. So we have 2x is equal to 4. And we can, from here, we divide both sides by 2. 2 goes into 2 one times. So this is 1x is equal to 4 divided by 2 is 2. 1 times x is x. So we have our x is equal to 2 is our critical point. So since we find the critical point, the next step is we have to find f prime prime of x. That is the second derivative. We already have our f prime of x. So we already have our f prime of x, which is our f prime of x, our first derivative, which we get, which is 2x minus 4. So if you want to find this f prime prime of x, is just to differentiate this. So this is 2 and constant. So this will just be 2. And this is minus 4. So this is 2. This is minus 4. If we differentiate it, it is 0. So our f prime prime of x is 2. And the next is to substitute x equal to 2 here. So f prime prime of 2. But since this is just 2, it doesn't have an x here, so it will just still be 2. So we can see that this f prime prime of 2 is greater than 0. So that's why we have this function has only, we have a local minima. It only have a local minima since it's greater than 0. And this local minima is at x equal to 2. And if you want to find the other point, we can write our f of 2. And this is just, we know our f of x is equal to x squared minus 4x. So f of 2 is wherever we have x, we substitute with 2. 2 squared minus 4 times 2. And 2 times 2, this is 4 minus 8. And this is minus 4. So our local minima is at 2 and minus 8. So that's when we have our local minima. So but no maxima, since we have only 1 point and it's always at minus 2. And the reason is that the plot for this function is like this. If you want to plot this function, is something like this. It's U-shape, so it have only minimum. It doesn't have maximum. So now we want to find all the local extrema of the following function. F of x is equal to this function. So the first step is, let's write it down. x cubed minus 3x squared minus 9x plus 5. So we want to find the local extrema, minimum, and maximum. So the first step is to differentiate it. If we differentiate x cubed, it's just 3x squared. We have been doing this. 3x squared, this is just 6x minus 9x is just 9. And this is constant, it will be 0. So then the next step is let this to be equal to 0. Let's 3x squared minus 6x minus 9 to be equal to 0. If you want to solve this, we can use factorization method, which is we multiply this 3 by 9. If we multiply 3 times minus 9, this is minus 27. So we have to find the numbers that if you multiply them, we get minus 27. If you add them, we get minus 6. And I think these are 3 and minus 9 because 3 minus 9 is minus 6. 3 times minus 9 is minus 27. Then we write here 3x. Then we have 3 and minus 9 plus 3x, then minus 9x minus 9 equal to 0. So I put the values here. So instead of minus 6x, I just substitute this 3 and minus 9x. And if you see, if you add 3 minus 6x, you will still get back your equation. So if I have this here, I have 3. In this first two terms, I have 3x. 3x can go in each two. So I can factor out 3x, and here I'll have x. 3x squared divided by x. Here 3x divided by 3x is just 1. And here I can factor out 9. I have 9 everywhere, so I can factor out 9. And this will be x. And here minus and minus, so it will be plus 1. It's equal to 0. 9 minus 9 divided by minus 9. So I have the two brackets are the same. That means I'm correct. So I can just have 3x minus 9 and x plus 1. I take those one outside, 3x and minus 9, and put them in bracket and take only one of these two brackets and say equal to 0. So this implies that 3x minus 9 equal to 0 and x plus 1 equal to 0. And from here, if I want to solve this, I can add 9 to both sides so that I get 3x is equal to 9 or x is equal to minus 1. So solving this one again, I have 3x is equal to 9, x equal to minus 1. I can divide both sides by 3. 3 goes into 3, 1. 1x is just x, so 9 divided by 3 is 3, so x is equal to 3, x is equal to minus 1. So, and these two are my critical points. So now I need to find among this critical point which one is the local extrema and which one is the maxima. So to find the extrema, then I have to find the second derivative. So I already have the first derivative, which is 3x squared minus 6x minus 9. Then the second derivative f prime prime of x is just to differentiate this. I take this 2 times 3, which is 6. X 2 minus this 2 minus 1 is 1, so this just 6x minus here is just 6 and x, so it will just be the constant 6. 9 is constant, so it will be 0. So f prime prime of x is 6x minus 6. So the next is I have this, then I will substitute my critical points. So substitute the critical point. So the first one is, let's substitute the first one at 3, f prime prime of 3. So in this function, so this is this. Instead of x, I put 3 there. For instead of this x, I will substitute 3. So I'll have 6 times 3 minus 6, and this is 6 times 3 is 18 minus 6, and this is 12. And 12 is greater than 0. So I know 3 is, so x equal to 3 is local. Since it's greater than 0, it's minima. If it's less than 0, maxima. So then the next is to substitute the other critical point, which is x equal to minus 1. So this is 6. Instead of this x, I substitute minus 1 minus 6. So this is 6 times minus 1, which is minus 6 minus 6. Then this is minus 12. So, and this is equal to minus 12, which is less than 0. So x is equal to minus 1 is local maxima. And if I want to draw this, let me find a space to draw this. Maybe I can even draw it here. So if I want to sketch this, this is just like this. This is s cube. So I have my point at minus 1 and maybe somewhere here 0, somewhere here at 3. So at 3 I have the minima here. At minus 1 I have the maxima. So I just have something like this, where the minimum is here and the maximum is here. So an inflection point are points on the curve where the function changes its concativity. So we have a concave up and concave down. So if you have this, this is what we call concave up. And if you have this, this is what we call concave down. So the inflection point is the point where the curve switch from being concave up to concave down or vice versa. And mathematically we say where the second derivative is 0. So for instance, if you have this, if you look at this plot, so you can see we have a concave up like this, and we have a kind of concave down also like this. We have a concave down something like this, and we have a concave up something like this. So the point of inflection is somewhere around this point where the graph change from being concave up maybe to concave down. So so that's what we call the point of inflection. And mathematically, if you want to find this, just take the second derivative, find the second derivative and equate it to 0, then find your x. So let's solve some example. Find the inflection point of this f of x equal to s cubed and this. So we just write our f of x is equal to s cubed minus 3x squared plus 1. So then f here. Then the next is find f prime of x, first derivative, and then this is the first derivative is here is 3. We take this 3 here, x3 minus 1 minus 3x. Sorry, we take this 2 here, 2 minus 1 plus this one, so its derivative is 0. So this is 3x squared minus 6x. So then the second derivative of x is we take the derivative of this 3x squared minus 6x. So we have 3x squared. We take this 2 here and we subtract 1 minus, since it is 6x, so we just take the constant 6. And this is just 6x power 1 minus 6, which is just 6x minus 6. So to find the point of inflection, we say we let f prime prime of x, which is equal to 6x minus 6 to be equal to 0. Then we solve this. So you have 6x minus 6 equal to 0. We add, to solve it, we add 6 to both sides. So it's 6x minus 6 plus 6 is equal to 0 plus 6. So it's equal to 0 plus 6. So we have 6x minus 6 plus 6 is 0. 0 plus 6 is 6. So we have 6x is equal to 6. Then we divide both sides by 6. 6 goes into 6, 1. So we have 1x is equal to 6 divided by 6 is 1. So 1x is equal to 1. 1x is just x. So x is equal to 1. So this is the point of inflection. So the point of inflection is at x equal to 1, which if we want to write the coordinate, we substitute x equal to 1 into our original equation. Original equation is f of x is equal to s cubed minus 3x squared plus 1. So f of 1 is 1 cubed minus 3 times 1 square plus 1. So this is 1 minus, this is just 3 plus 1. And this is 1 minus 3 minus 2 plus 1 is just minus 1. So the point of inflection is just at x is 1 and f of x is minus 1. So in this example, we want to find point of inflection of h of x is equal to minus x cubed minus x squared. So first, we write our h of x is equal to minus 2x cubed minus x squared. Then h prime of x is just equal to, we multiply 3 and 2 minus 2, we multiply this by 3, x3 minus 1 minus, we take 2 here, x2 minus 1, this just this and this is minus 6 x squared, and this is minus just 2x. So this is h prime of x. Then we differentiate this again, h prime prime of x, this is minus 6, we take this 2 here, is 2x, 2 minus 1 minus, this is just 2 and x power 1, so we take the constant 2. So then our h prime of x will just be, this 6 times 2 is minus 12, x minus 2. Because 2 minus 1 here is just 1, so it's just x power 1, which is this. So to find the point of inflection, we let h prime prime of x to be equal to 0. This implies minus 12x minus 2 equal to 0. So we add 2 to both sides, so we have minus 12x minus 2 plus 2 is equal to 0 plus 2. So we add the 2 so that to remove this minus 2. So we'll just have be left with minus 12x minus 2 plus 2 is 0 is equal to 2. So we have minus 12x is equal to 2. So we have minus 12x is equal to 2. We divide both sides by minus 12, and this goes into this once, and x we have is equal to 2 over minus 12, and 2 goes into here 1, 2 go into here 6, so over minus 6, and this we can even take the minus up, x is equal to minus 1 over 6. So this is the point of so the point of inflection is at x equal to minus 6. So that's our point of inflection at that point.